Hi everybody, welcome back to chapter 5. Today we're covering, in this video we're covering section 5.2, which deals with verifying trigonometric identities. Okay, so that's the objective. Okay, so what we're going to do in this section, we're going to study techniques for verifying identities. So remember, a conditional equation is an equation that is true for only some of the values in its domain. So let's say, for example, the conditional equation sine of x is equal to 0 is only true for multiples of pi. So x equals n pi, where n is an integer. So when you find these values, you're solving an equation. However, an equation that's true for all real values in the domain of the variable is an identity. So for example, this equation, sine squared of x is equal to 1 minus cosine squared of x is true for all real numbers x. So it's an identity. So let's talk about verifying trigonometric identities. Now, even though there are similarities to an equation, verifying a trigonometric equation as an identity, that it's an identity, is different than solving an equation, because there's no well-defined set of rules to follow. Okay, and the best way to do these is just to practice. So here's some guidelines to verify identities. You work with one side of the equation at a time. So usually what happens is you have an equation and you want to verify that that's true. So you pick one of the sides and you do things to it. You use properties and things like that to get it to look like the other side. Okay, so usually it's better to work with the more complicated side first, because then you can simplify it to look like the other side. So one of the things we do, we look for opportunities to factor, to either add fractions, square a binomial, or create a denominator that's just a single term, a binomial denominator. Another thing that you should look for is opportunities to use the identities, the fundamentals. So take a note of what functions are in the final expression that you want. In other words, the other side of the equation. Sines and cosines pair up well, so do secants and tangents, and cosecants and cotangents. And if all of this does not help, try just converting everything to sine and cosine. So, and the last tip is to always try something. Even making an attempt that leads to a dead end can help you figure out, something new. At least you'll know, hey, that didn't work. So it's really fun. It's a really useful process when you need to change an expression into a form that's more useful algebraically. When you verify an identity, you can't assume the two sides are equal, because you're trying to show that they are equal. Okay, so that's why since we're showing that they're equal, you can't use operations like adding to both sides, or I'm doing this to both sides of the equation, because you're not solving. You're basically verifying that one side is equal to the other. Okay, so I'll show you what I mean here. Example 1. Let's verify that secant squared of theta minus 1 over secant squared is equal to sine squared. So what we do is we're going to just take the left side and try to see if we can make it look like the right side. So the left side, I'm going to replace secant squared with tangent squared plus 1, and then substitute that into the numerator. I get tangent squared theta plus 1 minus 1. Then I just get tangent squared on the top, secant squared on the bottom. And I rewrite secant, the next step, I rewrite secant squared as cosine squared, right? Because secant squared was in the denominator. And 1 over secant squared is just cosine squared, okay? Then I can rewrite tangent squared as sine squared over cosine squared, right? That's the quotient identity. So if I write that, notice what happens to the cosine squareds. They cancel out, yeah? And that leaves me with what I wanted, which is sine squared, okay? So I verified it. So how did I verify it? I started with the left side, and I used the trig identities to simplify until I got exactly what was on the right side. Okay, here's one we can use using combining fractions. Let's verify that 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha is equal to 2 secant squared alpha. Okay, so when we add the fractions, we need to do common denominator. So multiplying the first fraction by 1 plus alpha and then the second one by 1 minus alpha, we can combine them together and you get 1 plus sine of alpha plus 1 minus sine of alpha on the numerator all over the common denominator, which is now 1 minus sine of alpha quantity times the quantity 1 plus sine of alpha. Okay, so then when you simplify, notice that on the numerator, the signs cancel out, and you get 1 plus 1, which is 2. And then we can also, the next step would be to use the Pythagorean identity, because 1 minus sine squared is nothing but cosine squared. Okay, so now I have 2 over cosine squared. But what's 1 over cosine squared? That's the same as saying secant squared. So that's the reciprocal identity, and boom, we've shown it. We've proved it. We've shown that this identity is correct. All right, let's try the next one. Let's verify that tangent squared of x plus 1 cosine squared of x minus 1 is equal to negative tangent squared of x. So let's apply the identities. Let's take the more complicated side, which is tan squared x plus 1, tan cosine squared x minus 1. And let's use the identities. Tangent squared of x plus 1 is equal to secant squared, and cosine squared of x minus 1 is equal to negative sine squared of x. You can find this by manipulating sine squared plus cosine squared equals 1 to the way that, till you get cosine squared of x on one side, you'll get negative sine squared of x on the other side. Okay, now that I have secant squared of x times the negative sine squared, I can rewrite secant squared as 1 over cosine squared, because that's the reciprocal, right? I can write it in terms of sine cosine. But what is that? Okay, so then I get negative sine squared over cosine squared. But what's sine squared over cosine squared, right? That's just tangent squared, right? Because you have sine of x over cosine x is tangent, and then it's raised to the power 2, so it's negative tangent squared. This rule of exponents part, you didn't necessarily have to write that out like that. You could have just gone ahead and done tangent squared. It's fine. But it's good to see that that's why, though. Okay. All right, so let's do example 4, converting to sines and cosines. That's one of the ways you can do it. So let's verify that tangent plus cotangent is equal to secant cosecant. So the left side, let's write it as sines and cosines. So on the left side, you get sine over cosine plus cosine over sine. So if we add these two together, what's the common denominator? It has to be sine cosine. So the first fraction on the right side, sine of x over cosine x, we're going to multiply top and bottom by sine. And then on the second part, we're going to multiply cosine over sine by cosine. Okay? So then that's going to give us sine squared plus cosine squared on the top in the numerator. And on the bottom, the common denominator of cosine of x, sine of x. Okay? But what's sine squared plus cosine squared? That's just 1, yeah? Okay? So we have 1 over cosine x sine of x. That's the same as saying 1 over cosine x times 1 over sine of x. But what is that? 1 over cosine x is secant x, and 1 over sine of x is cosecant x. And that's what we wanted to show, so we're good. All right, so example 5 says verify this identity. Secant y plus tangent y is equal to cosine y over 1 minus sine of y. And you might think like, well, wait a minute, how am I gonna do this one? Well, let's choose the right side because we can make a denominator, we can simplify by multiplying by the 1 plus sine of y, and we did that earlier. So if we do that here, so taking the right hand side now, let's multiply top and bottom by 1 plus sine y. In the denominator, we're gonna get 1 minus sine squared y because of difference of squares, right? And then on the top, if we distribute, we get cosine of y plus cosine sine y. Okay, and then 1 minus sine squared y is just cosine squared y. So we write that down, and you get the same thing on the top. So then let's split them up as into two fractions. We get cosine y over cosine squared plus cosine y sine y over cosine squared y. Okay, so that's the, let's see, 1, 2, 3, 4th line right there. And if we simplify, right, cosine y over cosine squared simplifies to become 1 over cosine y. And if you cancel out the cosines and the second part, you just get sine y cosine y. But what does that reduce to? 1 over cosine y is just secant of y, and sine y over cosine y becomes tangent of y. So there you go, we have verified the identity. Okay, example 6. Let's do another one. This is an example of verifying working with each side separately. Okay, so in this case, we would get, let's say we have cotangent squared of theta over 1 plus cosecant theta. And then on the right-hand side, we have 1 minus sine of theta over sine of theta. Okay, fine. So then let's start with the left side. So on the left side, we have cotangent squared theta over 1 plus cosecant. So we do this simple thing where we write cotangent squared as cosecant squared theta minus 1 because that's the Pythagorean identity. Cotangent squared plus 1 equals cosecant squared. So that's the first line. Then you know that that's difference of 2 squares, so we write that difference of 2 squares. So we write cosecant, we can factor it as cosecant theta minus 1, cosecant theta plus 1. Then the denominator cancels and the numerator cancels, and you're left with cosecant theta minus 1. Now from here, we could have, there's two things we could do. From here, we could have written it as 1 over sine minus 1, and then we would have done a common denominator, and you would get the identity. You just really needed one more step. But you could also go by the right-hand side and say, okay, 1 minus sine theta over sine of theta is equal to 1 over sine minus sine of theta over sine of theta, and that simplifies to cosecant theta minus 1. So this is one way to do it, but you could have also just gone straight through, okay? But yeah, it's verified because both sides are equal to cosecant theta minus 1. Okay, so let's do some last examples from calculus. Exciting. So let's verify this identity. A, tangent to the fourth x. We want to verify that it's equal to tangent squared secant squared minus tangent squared x. So first let's write them, so let's do A first. So A, tangent fourth x equals, let's write that as separate factor. So we're just working with the left side first. So that becomes tangent squared. And tangent squared of x is equal to secant squared of x minus 1. That's one of the Pythagorean identities. And then we're going to replace that. Okay, so tangent squared is equal to secant squared x minus 1. Then by distribution property, we get tangent squared x, secant squared x minus tangent squared x. So that's it. We've verified it. We could have also gone the other direction, but we're good. So let's look at B. So we have sine cubed x cosine to the fourth x, or cosine of x to the fourth power, is equal to parentheses the quantity cosine to the power 4x, right? Or cosine of x to the fourth power minus cosine of x to the sixth power, n parenthesis or n quantity times sine of x. So let's start with the left-hand side. So if we rewrite that and we write as separate factors, when we write sine squared of x times cosine to the fourth power of x, cosine of x to the fourth power times sine of x. We can write that because sine squared times sine equals sine cubed. And next, we can substitute 1 minus cosine squared for sine squared, right, and leave everything else the same. And then if we distribute the cosine to the fourth power, we get cosine to the fourth x minus cosine of x to the sixth power, and that's what we wanted. So that was a really quick one. So there's just like different strategies. So this one here, cosine to the fourth times cotangent is equal to cosecant squared x times parenthesis cotangent x plus cotangent cube x of x cubed. So if we write these out as separate factors, usually you write as separate factors when you either want to use just the reciprocal identity or the Pythagorean identity. That's usually how that works. So cosecant to the fourth can be written as cosecant squared times cosecant squared x cotangent x. So then let's replace the middle one with 1 plus cotangent squared x, because that's the Pythagorean identity. And then let's distribute on the right-hand side the cotangent of x. So then you get finally cosecant squared of x times the quantity, cotangent x plus cotangent cubed x. And that's really what you wanted. So that was it. That was like a two-stepper. Okay, cool. So that's it for this section. 1 through 19 odd, 29, and here are some ones that are connected to or related to the problems that we've just talked about. So good luck, and I will see you guys on the next video.